Hi everybody, welcome to Soft Earth Chalk Talk number 5. We're entering the parts of the series where there's like these contradictory chapters, right? So last chapter was the Earth is fragile, and today's chapter is the Earth is resilient. So I want to remind us just a little bit about something about fragility. I gave a definition that, while relying on your intuitive or lay person feeling of what fragility was, also defined it from a materials context. And the important part, just to remind ourselves about the fragile part of Earth materials, what I really mean is that they don't stay how you put them. What I mean by that is that they don't stay in the same state, right? So when we think about a material that is fragile in a materials mechanical context, it may look solid-like to us, like the pile of sand, but actually the particles are not going to stay in the configuration that we left them in. And so while if I put the sand pile on the table today, I expect it'll be in the same place next month, next year, but the particles in there, the sand grains, will not stay how we put them in the pile, right? So the best way to think about this fragility thing is really that these are materials that are sort of deformable even at, the configurations of them are deformable even at like infinitesimal stresses, okay? So today now we're talking about resilience, right? And it's supposed to have like a little paradox for you of like, how can these materials be both fragile and resilient at the same time? How, right? Yes. Well, today you're going to learn that, right? And Paulo always likes me to do some key points. I like to go through them, but I don't like to write too many words, right? But I'll just give you some key points right now before we get lost. One is that Earth materials evolve. And by this, I actually mean that I want you to think about Earth materials in a similar way to how you might think about biological organisms or ecosystems, right? That these are materials that have components that exist, are selected for, and can withstand the stresses of the environment under which they persist, right? So when we go outside and we see soil outside, we may not expect that the same grains of soil are going to be in the same place next year or 10 years from now, but we certainly expect that soil will persist and be there, right? So I want you to think about that there are selective pressures that are driving the evolution of Earth materials, and that when we encounter Earth materials in a given environment, that those are materials that evolved under the stresses of that environment. Hopefully that makes some sense. So, like ecosystems, then, there's another component, which is that some Earth materials, and especially some aspects of soils, are actually complex networks, okay? They're hierarchical, where they're made of different materials that are connected across scales. The interconnection across scales makes them behave in unexpected ways, but it can also make them resilient to a whole range of disturbances, right? So the third point that I want to make then, which hopefully will come out, is this adage, more is different. And by more is different, I mean when we have these complex materials that are networked and hierarchical that withstand this barrage of stresses, sounds like a complicated system. It has a bunch of different ingredients mixed together. The idea of more is different, though, from this famous Anderson piece, which kind of kicked off a different way of thinking about condensed matter and materials, is that when you take a bunch of things and mix them together, if your expectation is it's just like a simple system but more complicated, that's not quite true. Actually, that when you take a bunch of different components and put them together in a mixture, if they interact, they can interact in interesting ways, and that totally unexpected behaviors can emerge, right? And so I want us to understand that the richness and complexity of natural Earth materials can also give rise to unexpectedly rich behaviors. And both celebrating that those different ingredients together make complex behaviors, while also believing that you could strip it down to some essence and hopefully understand physically is complicated, but that's what we want to try and do. All right, so with those concepts in mind, I want to think about two earth materials. I'm going to start with the example of ice because I think maybe it's more obvious for people. But once we go through this exercise with ice, then we can start to think about it with soil. Okay. So if I asked you where on Earth do you find ice, right? So you could start by drawing the same phase diagram that I draw every single time, right? I always start every lecture pretty much. I didn't start with a drawing of the Earth and plate tectonics this time, but we are going to draw the same phase diagram. This is a phase diagram for water, right? I don't remember the numbers except for like 0, obviously. So I'm not going to draw them out, right? But remember here that we have solid, we have liquid, we have gas, we have this critical point over here, which is interesting that we return to from time to time, right? So we understand that over here in this range of pressure and temperature conditions is where ice can exist in a thermodynamic sense, right? And then we understand that on Earth, we only have a certain range of pressures and temperatures on the planet. So in a lab, we might be able to go down to like absolute 0 or pump pressure way down. But out there in the natural world, we occupy some sliver of this, right? So you can think about it. If you wanted to know where on Earth might you find ice, you might start naively with a thermodynamic definition of solid water, find where the range of temperature and pressure conditions where the range of temperature and pressure on Earth overlaps with the range of the solid phase in the thermodynamic diagram, right? And you would go look for that, right? So temperature, we understand. Temperature is a function of altitude and let's just say latitude for simplicity, right? So you can go up or down toward the poles and you expect to see ice. So if you draw planet Earth, you expect that there's regions at the top and bottom, right, where it's sufficiently cold, integrated over whatever you want, a year, a decade, whatever, right, in order that the temperatures are sufficiently cold when averaged over suitable length scales, that ice can persist. We also, though, understand that there's this altitude feature, right, which, of course, altitude, the pressure variation over here is primarily a function of altitude also. So when we play this out spatially on planet Earth, we understand that both temperature and pressure are going to be functions of altitude. So in Earth space, pressure and temperature are not independent from each other, right? They co-vary. But practically, we could just say, well, let's say that I have a mountain range that is sitting here at the equator, but if I'm suitably high, temperatures are suitably cool, that I could still have ice persist, right? So we have, for now, still some tropical glaciers, and they do exist, right? And so, you know, when you think about this in a schematic kind of way, right? We now know, right? So here is the mountain, and we're going to say that there's ice up here, right? But when we say that there's ice up here, there's ice that's sitting here with some finite thickness to it. Sorry for my terrible drawing, right? But the ice has some finite thickness to it. Here's the thing, though, is that what I want us to think of is that the ice existing on planet Earth is in a state of dynamic stability, right? So you can look at this phase diagram and you would say, sure, if I understood this phase diagram, implicit in this phase diagram is that pressure and temperature is constant, right? So at one given pressure and one given temperature, I can look and I can say, do I have ice? But on planet Earth, anywhere that we have ice, even in the coldest places, what I want you to understand is it's not a block of ice that is sitting there stably. It's that there are places where ice is being created, right? So if we look up here, we have snow falling, right? Making little snowflakes that are adding mass to the ice. We also have a sun which is shining, and so even under cold temperatures, we're getting ablation of that ice. And then we have the ice is flowing, as we talked about before, and so at some point it's going to get down to a place where the temperature is hot enough that the ice is going to melt, right? And become a liquid and flow away in a river. In other words, I want you to understand that the places that we see ice, we should not think of that ice as stable. So we can use the phase diagram to guide us, but I want us to understand that this is a population. This is a collection of materials, ice grains smashed together. There are new ones being added, and there are ones that are turning to the liquid phase. This ice is also flowing, it's cracking, right? And so this is a population, and it is stable in the sense that on average it exists, but I don't want you to think that this is a stable collection of particles, right? So if we accept that simple definition of like a dynamic stability, then what you would say is that the phase diagram is helpful for us on average, but it doesn't provide a complete picture. So now let us think about, I didn't get an eraser out. Let's think about soil, which is a little more complicated. And I think that rather than start with the phase diagram because we don't have one, I'm going to start with a sketch like that of the landscape, right? So imagine that we have a mountain. The mountain is made of rock. Of course, we now know that that rock is all fractured and breaking apart. And then on top of that, there's a blanket of soil. I draw it as a mountain, but you don't need a very tall mountain. We're in Philadelphia right now. If you just go to Wissahickon Park, you can stand at the bottom of the Wissahickon Valley, where there's a river, and you see a nice, rich, thick soil profile. But if you just walk up the hillside, you can walk up to the top, where you will see the soil thins to non-existence, and there's a rock outcrop there, right? So what I want us to understand is that you look at a hill or a mountain, and you see that there's soil in some places, but up usually at the top, and the higher and steeper it is, the more likely you are to encounter this. You can find a place where the soil is not. And so this is telling you something of the existence space of soil, okay? It is in some places, it's not in other places, and what is it that allows soil to accumulate, and why does it accumulate ever more as you go down the slope, right? And the argument I'm going to make, like everything else, is a cartoon, right? But let's start with something similar like temperature and altitude. So altitude and pressure go together, but atmospheric pressure doesn't really affect soil development that much. It doesn't vary enough, but altitude varies a lot, right? And so you could think about altitude and temperature, which, as I mentioned, they can co-vary, of course, but I draw a line here. So first of all, there can well be places where if the temperature essentially never gets warm enough to sustain liquid water, development of plants and life and soil and all that kind of thing, there are suitably cold places where it is very hard to develop soil, right? So you can go to places in Antarctica and you can see ground up sand that's been ground up even smaller, like glacial powder, but you're not going to see, like the soil scientists always tell you, if it doesn't have organic material and clay particles, it's not a rich thing, it's not a soil, right? So by this, I mean that we could be suitably cold where you can grind rock into powder, but you're not going to have the chemical reactions and biological actions that make a holistic soil. You can also imagine that there are some altitudes that are so high, and we're going to talk about why that might be an effect in a little bit, right? Where beyond which you might not expect to have soil. Like I said, I'll get to that in a minute. And so then you could imagine drawing, I have no reason to draw the curve this way, okay? That curve could be drawn any old way, right? But you can imagine that there is a regime within which soil can live. And if you're too cold, you're not going to have the processes that break down rock and produce the material that generates soil. And if you're too high, you might not do it. By the way, why if you're too high? I'm just going to hint at it right now. If we're thinking about the mountain example, right, we have a situation where uplift is pushing the mountain up by tectonic convergence. We talked about that a little bit, right? We know that erosion is taking material down. I haven't given you any equations, but you might imagine that the steeper the slopes, the more erosion you might have. There's also a time scale that it takes to weather. Like the stuff that makes the soil, the raw material for that is the rock. And so the rock has to physically break apart. It also has to chemically dissolve in order to turn to pieces and make the matrix that biology can start to populate and take hold in. And so there's a time scale of weathering, which is really the time scale that it takes to convert rock to soil. And if that time scale is really long, then anytime a particle gets turned into soil, it's just going to get transported away. So we're going to return to that idea. But just because I don't want to leave you hanging about why this altitude thing, it turns out that as you go higher up and it gets colder and colder, you both slow the time scale of weathering, and there's a time scale of erosion, a time that it takes to remove the material, which ultimately is driven by uplift. So the more you push up, the steeper you get, the stronger the potential energy, the more erosion there is. And so down here, what I want you to think about is that when we're in this soily place down here, there's a time scale of weathering and there's a time scale of erosion. And if the time scale of weathering is short compared to the time scale of erosion, you're making soil faster than it can be eroded away. So if this is less than 1, this is a place where soil can exist, right? And up here, you're in a situation where the time scale of weathering compared to the time scale of erosion is greater than 1, and you will have no soil. So obviously by abstracting things like weathering and erosion down to timescales and not even telling you where they come from, this is a cartoon argument, right? But I want you to be thinking about it that anything that will affect the rate at which you turn rock into soil or the rate at which those materials get transported away is going to affect the balance that determines whether or not you have soil, right? Now, you could also imagine making a drawing that has precipitation in it, right? So I had hinted that we have something like weathering. Ultimately, you need water to dissolve some chemical elements in rock. You also need water in order for biological things to grow on and use, and they contribute organic material and binding to the soil. So you could also imagine a situation, let's just keep it easy and make another 2-dimensional diagram rather than try to make 3-dimensional diagrams. But where you have like temperature and precipitation. And now it's easy to imagine that just like there's a minimum temperature at which you might expect to be able to start producing soil, you need a certain amount of precipitation to do it, right? So in the driest of deserts, what you see is sand and dust. The soil science people give a vague name to like these materials that are like trying to be a soil but barely can, right? But for most purposes of what we consider a soil, which I'm going to get to in terms of its complexity, this complex hierarchical material, it's not that, right? Below a certain amount of precipitation, we're not going to get complex soils, right? And so again, now you could imagine drawing some diagram that's like, well, I need to be above a certain precipitation level and I need to be above a certain temperature level. And so who knows what that line looks like? You know, I'll just make a random one, right? But you'd be like, here we are, like this, there's some precipitation temperature range where soil can exist, okay? So I'm drawing these like phase diagrams, but I want us to understand clearly now. These are complex materials, physical, chemical, and biological all together. There is no thermodynamic equivalent phase diagram that we can draw, right? I'm not drawing even a phase diagram. I'm just drawing variables that are relevant to the Earth to have us, you know, try to understand these things, right? Now, if I come back here and I think about this soil, I want us to think again, though, about that this is in some kind of dynamic stability, right? So we know that we have in this soil, the sun shines and goes down, the temperature goes up and down. We know that right? It rains on that soil. We know that we have things like earthquake shaking it. So when we think about the soil on the mountainside, it is subjected to a barrage of stresses at a barrage of scale, or a huge range of scales, huge range of frequencies, amplitudes, right? And so when we think about soil existing on this landscape, it is not only formed under these conditions with these timescales, but it is somehow able to withstand this barrage of stresses. Indeed, some of these stresses, like the rain and the sun and all that, are forming the soil. And they're also creating stresses that remove the soil and transport it away, right? And so there's a situation where there's a conversion of rock to soil, and there's a transportation of the soil and removal off the mountainside by creep, by landsliding, by some combination of those things, right? And so the soil is not stable in the sense that it's moving all the time. It's fragile, it's creeping, and occasionally it landslides. But it's pattern stable in the sense that the soil that's here today, I expect that when I return next year or 10 years from now, I will find soil in that place, right? And so it is this material that has evolved under these environmental stresses, and it persists under those environmental stresses. And this may sound obvious, but the materials that you see in that soil are materials that can survive there. Okay? There are other materials that Earth makes that you don't find here, right? They're either transported out or they don't get produced here, right? And so that's the concept that we want to explore, is that the aspect of evolution and resilience is that these materials formed under these conditions and they are resilient to the stresses under which they evolved, right? So we have this idea, I guess I would say that it's evolution under a selective pressure. So if it's a soil, this is a little abstract, okay? Soil's complicated. It has a lot of factors I'm not writing out. And so let us think about this idea in a little simpler of a system, okay? So I like sand dunes. Surveying the room of people who like sand dunes. Okay, a couple of you. Oh, more, okay, majority, not for fun. Okay, okay.
That's why
Okay.
it's on white sands.
So, okay, I'm gonna draw a field of sand dunes, right? A typical beautiful sand dune is these boomerang-shaped Barkhan dunes, as we call them. We're looking from above, so you can look at maps of places in the desert, and the wind blows, in this case, from left to right. The sand doesn't just blow as a loose sheet. It organizes itself into these piles. These piles get beautifully sculpted and streamlined as the wind interacts with them. And I'm looking at them from above. If you were to take a cross-section through a sand dune, I'm exaggerating it vertically, but it looks kind of like this, okay? So we're looking at this from the side. What will happen is that the wind, right? So you have a wind profile, slower at the bottom, faster above. The wind comes and starts flowing over and interacting with the sand dune. These streamlines converge, which means that the flow speeds up. So as the flow speeds up, it picks up particles, right? So sand grains get picked up here. They hop, these short hops. When they get to the other side, they're now shielded from the wind, right? So they're shielded from the wind. The grains hop over the edge. They deposit somewhere on this pile. It's a sand pile. So remember, you keep raining down grains at the top. What's going to happen is it's going to avalanche down. And so with these sand dunes, you have the wind-facing side, where the grains are transported directly by the wind, and the slope is lower and streamlined. And then you have this shielded side over here. And on the shielded side, the grains can only move down slope by avalanching. So here, you have a pile at the angle of repose that we've talked about before, okay? So, you see sand dunes, they're made of sand. That seems obvious. What I want to tell you, though, is that the conditions under which sand dunes exist are conditions where the stress that comes, in this case, from the fluid, from the wind, where the fluid stress is 1 plus epsilon times critical. Remember, this just means epsilon is a small number, right? Small compared to 1. Remember, everything is threshold, and threshold is everything. When I see sand dunes, I can tell you for sure that under the winds that form them, the wind stress is just slightly above critical. Now, how can I know that? The way that I can know that is that if the sand grains were to get picked up and suspended and transported long distances by the flow, they would not get trapped in this protected zone behind the dune. And therefore, the sand grains would erode over the dune, but they would travel far away before they deposited. Okay? So, the existence of a sand dune tells you that the winds that blow most often and move the material are just close to threshold for that sand. If that were not the case, you wouldn't have sand dunes. Either the wind couldn't pick up the grains and they wouldn't pile up in the dunes in the first place, or the wind would suspend the grains, and when that happens, the sand dunes erode away. Right? So, we think about this then, is that one thing that you might notice if you're lucky enough to be in a desert when the wind blows is that when the wind is howling, there's this little film of sand grains along the bottom and they're just hopping. They're barely above threshold. But if there's dust around, really tiny particles like 10 micron sized particles that are coating the sand, they get shaken off when they collide. What you'll see often in these transport events is clouds of dust. Right? So, why do I bring that up? If you think about the tiny dust particles, for them, the wind that is blowing is way, way, way greater than critical, right? So when the wind blows, what happens is the small materials that get suspended, they get removed from the system and they go away. The particles that are too big to ever move don't make the dunes in the first place, and the dunes are composed of the material that is just barely mobile. What is that? How does that relate to this idea? This is a simpler system that says sand is the material that is resilient in this environment, right? We have this almost living thing called a dune. It migrates, it mutates, but it does not go away, right? So it is also a dynamic stability kind of thing. We only see dunes in dry environments, so we don't have soil. We don't have enough moisture to hold the grains together. So this is an extreme limit of dry areas, wind, and under those conditions, when we see sand dunes, we know that the wind is near threshold. By the way, this is really nice and convenient. It means I can go to Mars and I can just estimate what the size of the sand is, and I can tell you how strong the wind is. We actually did that in 2004, and nobody believed us, and they said the wind never gets that strong. But we saw sand dunes, and then the wind did get that strong, and we finally observed it on the surface of Mars, right? So, this is not true just for sand dunes, though. You remember the argument, right? The argument that I made for rivers in my terrible 2D to 3D meandering drawing, right? But remember that, sorry I made this so small, rivers are also organized, right? Remember that? To be just above the threshold of motion. How that plays out is if you go downstream in a river, let's imagine a profile of mountains and then a river that comes down. What you actually observe, right, is that the grains get progressively smaller as you go downstream in the river. Up here in the steep parts of the river, the materials that persist under those high slopes are just the largest particles, right? So when you go and you see big boulders at the top of the river, it's not that they never move. If you see them in the river, and if you see that they're rounded, for sure the river has moved them. But they get moved slowly and broken apart by fragmentation, and they get others that come in and replace them from the mountains tumbling down, right? And so this particle here, these large boulders, are the materials that are resilient under the kind of stresses up here. These finer particles that you find down the river, they're up here too. But the current is too swift for them to deposit, right? So up at the top where the energy's high, the big particles persist in that landscape. The sand and the clay and all of that washes down and it doesn't deposit in the riverbed. And as you slowly decrease energy going down, you see this selective transport and deposition. But at any point in the river, you can stand in there and say, oh, These are the particles that in this kind of current, in this kind of energy, are getting replaced at the same rate that they're being removed. So there's a dynamic stability maintaining that kind of material in that place. Okay? So let me meditate on sand for a minute, because I want to start to move into the area of complexity. So let's just imagine sand like you're at the beach, right? And you know that, I'm going to draw, careful, I'm going to draw a terrible foot, right? Okay, here's a foot, you know, like a Simpsons yellow, right? But here's a foot, and you're exerting a normal load on the sand, right? So we know that the sand can be soft or the sand can be packed, and so the response of the sand is not always the same. But if you jump up and down on the sand a lot, it might compact a little bit and eventually it stops. What you understand is that generally sand is a material that is pretty strong or resistant to compressive loads or normal loads, right? When I push down on sand, it pushes back hard, right? And even if in the beginning it's loose, if I jump on and I stand on it, I can compact it. And so sand is going to be strong to a stress that is compressive or acting down or normal to it, right? Now, if you come in with my terrible hand, right? But let's go into the sand and you try to pick one up, right? Yeah, sorry about my hand. You want to go to dry sand and you want to prise loose a pinch of that sand from the surface. It's like no effort at all, right? No effort at all. There is literally no force resisting you pulling a sand grain away, right? So when I want to push these sand grains down, all the sand grains are smashing into the other sand grains. In order to move the sand underneath me, it has to move other sand out of the way. And therefore, there's a lot of resistance to doing that. But if I go in and I want to pluck one of these sand grains loose, there's no resisting stress, okay? So I would say that sand is strong under this compressive load, and it is, I would say that it has no tensile strength. And I'm not going to be very mechanical. For us, tensile strength just means pulling things apart, okay? It's a purely frictional material. Purely frictional materials have no tensile strength to them. Now, we're going to stay at the beach, right? What do you do if you want to add tensile strength to it? Everybody knows what you want to do if you want to add tensile strength to it, right? This is what you do when you make a sandcastle, right? So, now you're going to see my beautiful castle, right? So, the sandcastle now, what do we do? First of all, I want you to understand that if the sand is capable of holding a vertical wall, a wall that is bigger than the angle of repose, right? Then there's for sure a stress, a tensile stress that wants to pull the sand grains on the wall away. So something is holding them back from just falling and collapsing down to the angle of repose, right? When this sand is dry, it wants to have, right? It just wants to have a pile like that at the angle of repose. So we have oversteepened it. So we've done something to enable it to build above its angle of repose. And that means we can calculate the forces. There is a tensile stress now that's trying to pull this thing apart. And where does it come from, right? So if we blow this up, right, now we have the situation where there's a sand grain and a sand grain, but between them is a liquid bridge of water, right? Now remember, water has surface tension, right? If you poke at the surface of water, you can see it deform and it pushes back on your finger. And if you're very careful just doing this with a cup of water, you can feel the resisting force pushing back on your finger, right? And so when a little bridge of water forms between these drops, when you try to pull the sand or between these sand grains, when you try to pull the sand grains apart, the deformation of that water surface exerts a stress by surface tension, and it's like a little spring that wants to pull it back. Now, surface tension is not that strong. It's not very hard for you to take 2 grains to do. An exercise you can do at home is just take 2 marbles, dry first, and pull them apart, and then dip them in water and put them back together. And you can see this water bridge on them, and you can pull them apart, and you can feel that it takes more force. It's not hard. But you add up those forces, and you do it for this grain, not only to the grain on one side, but this grain has a neighbor here, and a neighbor here, and a neighbor here, and it's 3 dimensions, so it has all these neighbors. And that adds up to quite a bit of extra strength, right? And so what we've done, when you think about tensile strength in granular materials, what I want you to think about is that tensile strength comes from cohesion, right? Or flip it around. Cohesion is the tensile strength that a material has even when there's no normal load on it. In fact, that's like if you're into like classic frictional stuff, that's like the more cool-on definition of cohesion, right? But for us, I just want you to think that cohesion is a resistance to pulling particles apart. Purely frictional things like sand have no resistance to pulling them apart. Add a little bit of water and you get a resistance to pulling them apart. So that's one way to do it, but it's not the only way to do it. So another common material that we encounter in soil, besides water being added to it, are clays. And I'm not going to go very deeply into clays here, but just for you to have an understanding about why they're different, I'm going to draw like a little clay particle here, okay? Essentially, you know, all surfaces of particles are charged, but for a massive sand grain, we talked about this a few lectures early on, sand grains are big, they have a lot of mass. Even though they have charges on their surface, the strength of those charges is weak compared to the mass of the grain. So sand grains interact with each other by friction, and even though they have surface charge, that doesn't really matter. That force is negligible. Clay particles are on the order of a couple microns. Technically, we say things smaller than 2 microns are clays, right? But mineralogically, clays are these little platelets, so they're tiny, they have a lot of surface area, and they have surface charge like other things do, but the difference between them is that sand grains are pretty much negatively charged everywhere. Clay particles, like the simplest clay I'm drawing here, kaolinite, they have negative faces, but they have positive edges. So what happens then is that if you get a bunch of clay particles together, and I'll just draw them now as like little plates, is that if the positive edges can find the negative faces, they're actually electrostatically attracted. And so they stick. So because of the charge heterogeneity and the small mass of clay particles, they actually stick together. And so if you take sand and you add clay to it, you get a cohesive material. If you take sand and you add water to it, you get a cohesive material. If you take sand and you add water plus clay, you get a more cohesive material, right? And so what I want us now to understand is that this adding of cohesion is not just a quantitative change in the material behavior of the soil, that there is a qualitative change. And this is one that we kind of know about already, right? So for a long time, we've built with earth materials, right? So humans have built with earth materials. And so have a bunch of other animals, right? And so when we do that, like, so I'll just draw like a terrible example, right? So let's imagine you have some like, you know, ye old looking adobe house, right? You can picture it, right? So some of the oldest structures that we have built by humans that are still around today, right, are made of earth. In fact, all of the oldest structures are made of earth. And the thing about these materials is that there was something about the material, which of course the raw ingredients are soil, right? There's something about that soil that if you added water to it enough, it would behave mechanically like a paste. So, you know, you can mold it and shape it, like paste or silly putty, and you can make bricks out of it or pile it in like a solid wall, but that when it dried, it becomes strong, right? So we already understand that there's this heterogeneous soil. We can add some water to it to manipulate its mechanical properties. We can build with it where it's workable, and then you let it dry and it becomes strong. But the other thing that happens is that when it becomes strong, it does also become brittle. We've talked about brittleness before. And so this material, as the soil that the building is built on top of gently consolidates and compacts by creep, which it's always going to be doing, then the building settles differentially. And so the building will develop cracks. But there's a remarkable thing, which is that you can add water to it again, you can hydrate it again, and you can actually patch these cracks over again, right? So, first of all, I want to talk about building with this material. Okay, so if you want to build a wall out of soil, we know that we can't just do it with sand, right? We can't make a vertical wall and hold it together, right? So, let's say that we want to build a wall with soil. Well, what we do know is that we want to have soil with sand in it, because the sand is strong under a compressive load. You know that if you tried to make a wall out of pure clay, it would be squishy, or if you dried it, you can do it and you can make it out of brick if you want, right? But if you're not going to be like drying it and making brick, right? We want to build walls. You have sand, and you know that under sand, it's compressed. There's strength under a normal load or a compressive load. But you know that there's no ability to withstand a tensile stress, right? So if you add clay particles inside of here, so you fill all the pore spaces. So you have a skeleton of sand. So when you push on it, there's this frictional skeleton that withstands the load. You fill in the gaps with another material. You add clay, which is like mortar, which is holding it together and allows it to withstand a tensile stress. And it's actually the combination of those two things together, leveraging the compressive strength of sand with the tensile strength of cohesive materials like clay. And when you put them together, you make a material that is strong to all the stresses that you need, right? And so we're leveraging the compression strength. We're leveraging the cohesion and the friction in order to build this way. All right? It is strong and it is resilient. Now, I want to give us another example about strength versus resilience, right? So now we're going to do another drawing. Let's think of, this is going to be a dam. So you're going to have to bear with me on my drawing, right? So let's say this is like a steep canyon wall right here. Oof, this is really bad. Hold on. I'm going to do this better. Well, let's just say that we have a dam. I don't need to draw the canyon wall right here, right? So we're holding back water back here, right? With our dam, there's a stream of water that is flowing away, whirling and swirling and doing its turbulent thing. So we build a dam to hold back a bunch of water. And if we look at it in profile, right, it looks like this. Here's the water being held back. So, by the way, dams get thicker as we go toward the bottom because the pressure that's acting on them is the pressure of the water, which is hydrostatic. The hydrostatic pressure increases linearly with depth. And so you can get away with not very thick material at the top, but you thicken as you go down because you have an increasing pressure, right? Just like the pressure you feel when you swim to the bottom of a swimming pool and it starts pushing on your ears, right? So you have to build a dam that is thick enough to withstand the hydrostatic stress here, okay? Now, the easiest way to do that at scale is to do it with cement. So we know that cement, of course, a lot of cement is earth materials. You take lime, you mix it with water, you fill it with particles. So it's not unlike this, right? But the mortar that you use is this lime, and you add water. There's a bunch of chemical reactions and other stuff that happen. But the point is that we know that we can mine earth materials, we can mix them together, and we can make a super strong material like cement, and we can use it at scale to build giant walls, and we make big dams out of it. Okay. So remember our little training that we did on strength of material solids, right? And we said that I'm going to think about the strength or stress of the material, the stress of material as a function of deformation, right? So this is strain over here. So if you think about it, it can either be that I'm taking a material, strain can be a strain that is defined by taking a material and deforming it, right? Shortening it under compression. Strain can be a shear strain where I take a material like this and I apply a stress to it that makes it deform this way, right? For us, strain is just the relative amount of deformation, right? And I know that if I take a material and I strain it under compression or under shear, that the resisting stress is increasing. And remember that for a simple elastic solid, it goes like this, it goes up until it doesn't, right? So this is the yield stress, the stress at which cement is going to break, and it's high, right? So cement is strong, breaks at a high stress. You figure out what the stress you need at the base of this thing, and you use the yield stress of cement, and you're off to the races. So cement is strong. Great. But what else is it? Brittle, right? Remember this part. This fact that beyond a critical loading, cement just cracks and falls apart means that if you shake it in the wrong way, it's going to catastrophically fall apart. One thing cement is not is resilient. So it can withstand a barrage of stresses, but when it starts to fall apart, it falls apart. Okay. So we build dams with cement. You know where they don't build dams with cement, even in America? In California. So they build dams in California with soil. Now, soil is weaker. So if you want to build an equivalent dam at an equivalent height with soil, you're building a dam with a lot more material. So it takes a lot of material to build earth dams. Earth dams also have water flowing through them and in them. You have to worry about that too, right? They're like almost literally living things, right? You have to like maintain them. You have to have some water but not too much water. So why would you build more than 100 meter dams out of soil in a rich state, in a rich country where we have plenty of cement around and that we love to build in cement? Because of earthquakes, right? It's not a problem we have to worry about over here, right? But over there, you have earthquakes. You have earthquakes and you shake the ground, you shake the dam, and you actually excite a bunch of different frequencies of deformation within the dam. And cement dams are known, and we have, unfortunately, sad evidence that they fall apart during earthquakes catastrophically, right? Now, what about the soil? So let's think about building this dam with a complex soil. So it's got big particles and small particles. It has frictional and cohesive resistance. Now, on the one hand, it is fragile. We put a soft material here, soil, right? And I tell you, soil never stays how you put it. Soft materials don't stay how you put them. That's what fragility is. So on the one hand, it is deforming, it is rearranging, it is changing its state all the time. On the other hand, you come along and you shake it, and when you shake it, some of this material starts to give way and move, but then it has this soft deformation that then some other material comes in from over here and fills it in. You have this connectedness through cohesion, and essentially what's happening is that the dams can actually self-heal. So you can shake them and it causes local instability, but those instabilities rearrange and it kind of settles into a new state. And that new state is just as stable as the old state, right? The downside of fragility is that you can't predict how things will rearrange. The upside is that there's an infinite number of configurations of particles that are equally stable. So the material can have a new configuration, but the same general stability. If we think about that mechanically, what is the soil is more like this, right? So the soil has a yield stress that is lower. It's not as strong, but it has this soft or ductile behavior which allows it to heal. And so soil can withstand this barrage of environmental stresses where brittle materials break. And this is, of course, in material science, this is always the compromise. With strength almost always comes brittleness, and with ductility almost always comes weakness, right? But soils exist in a bunch of states. And these are kind of the two end members, right? So think about now the soil not in a dam, but on a hillside, right? And so now we're going to draw our mountain, but we're going to draw it in profile, right? So here's our rock fracturing, getting cut up. Here's this well-developed soil blanket that maybe is thickening down toward the bottom. And of course, in a natural environment, growing on top of it are also a whole assortment of trees and shrubs and grasses and other things like this, right? And if you zoom in on what that soil looks like, right? So you have some big particles. Between those big particles are bridges of smaller particles, and between those smaller particles are bridges of even smaller particles. This is what aggregates are in soil, right? And then around all of that, you have like roots that go through and are looping around these materials, okay? So the first thing about this natural thriving soil in this healthy ecosystem environment is that it is hierarchical. By hierarchical, I mean there's particles within particles within particles. And if you go up in scale, beyond the scale of the particles, you have these like elastic ropes that are the roots that are themselves sort of holding particles together and acting like weird kinds of particles themselves, right? And so you have this hierarchical structure to the soil. That hierarchical structure, what I mean by that, right, is multiple scales. And the multiple scales interact with each other, right? So when you try to deform this material by pushing on it with a shovel or walking on it, you're activating responses of a bunch of different materials at a bunch of different scales that are also interacting with each other, right? And so this hierarchical multi-scale soil is complex. Now, in colloquial terms, remember we talked about like complex and complicated for some people are the same. But in science we make a distinction. Complicated is a system that is hard to understand because it has a lot of things in it. Complex is a system that is hard to understand because there are a few things in it, but the few things in it interact to produce an interesting unexpected response, right? So complex means that there are emergent behaviors that come from these interactions across scales that are unexpected, but that we might hope to discover and figure out. So soil is certainly complicated in some ways, but I also want to argue that it is complex, okay? I'm going to get back to that complexity after I take an aside on this brittle ductile difference with landslides, okay? So there are, by the way, natural materials in the earth, like soil, that respond like this, but it's not really rich soil. It's basically like if you have compacted, strong sand, it's mechanical responses like this. Okay? So, if we think about this in the context of landscapes, if we have a mountain range here that I'm kind of drawing in a perspective view, right? With a landslide on it. The simple soils, which are basically compacted sand and nothing else, the simple soils are brittle, and what that looks like at the landscape scale is that they make gigantic landslides that detach catastrophically, and the material that detaches from them flows and deposits nearby, okay? So simple soils that don't have that hierarchical nature, that don't have the roots and the clays and the organic material and the sand and the silt all mixed together, they elicit, when you wet them or when you shake them, they elicit a brittle response. They're strong and then they fail catastrophically. But we see another thing in more temperate environments. I'm actually going to leave that up there. So I'll just draw a compressed mountain range. In some environments, we see persisting these, what we call slow landslides. So you're looking at the soil and you see that there's an edge where the material is sliding. So it's moving downhill in here and it's not moving over here, right? But when you look inside the material, you see that it looks like it's oozing. It's kind of soft and crumply. It has these little ridges that look like a carpet when you squeeze it together. And so in complex soils, you have a ductile behavior mechanically, and that actually expresses itself in the landscape of these. These are landslides that are essentially continuously failing all the time, but they never catastrophically fall apart. They're just like living in this regime, right? So when you have complex soils, you actually have material that's failing all the time, but it's never failing catastrophically, right? Whereas the brittle, simple soils can accumulate damage and then they fail catastrophically, okay? And so there's this mechanical difference. And when we come back here, the way to think about it is that when we generate a landslide, what you have to do is localize failure. So imagine that what I'm saying is that, imagine it's a granular material, but there's a crack that's going to develop in the granular material and rip it apart. So when you have a catastrophic landslide, of course, the material is granular material, but what happens is that a crack is just able to rip right through it. So a crack localizes and it starts to open up in the material. In a complex material, when a crack starts to run through the material, sometimes it runs into sticky stuff that redirects the stress upward, and then it runs into a root that has some elasticity to it, and then that root activates some clay particles over here that push on and cause a local rearrangement in the sand. When you have a complex material, what it does is it delocalizes the stress. In a simple material, a crack can rip right through it. And in a multi-scale material, you're going to activate a bunch of different modes of response at a bunch of different scales. It kind of comes back to the noisy room with you shouting in it, right? This is a very noisy material, but that noise internally is going to dissipate stresses that you try to localize within it. And a simpler material, a stress that gets localized can propagate through it, right? So if we return to our mechanical picture now, and we actually think about this truly complex hierarchical soil, you can get strain responses that are actually like this, where like they never actually fail completely. So the stress might build and drop, but even after the stress drops, meaning that the material's starting to get activated and flow and deform more, it can catch itself. It's in a new configuration, and that new configuration is stable, and it can start accumulating deformation again, right? And so in truly complex materials, you can have mechanical responses that are unlike anything that you encounter in like a solid mechanics class, right? And so this multi-scale interaction, when I say that it's complex and I say that more is different, what I mean is that we can get qualitatively new mechanical responses in really multi-level hierarchical complex soils. And this kind of mechanical behavior is very resilient. If resilient in this case means that the material, it's like it keeps deforming as you're stressing it, but it never falls apart, right? It's like, you're getting attacked by somebody bigger than you, but you have all the stamina to keep dancing and you never get knocked down, right? And so this material is resilient. It is not the strongest, but it is a material that never fails. It just gives way. It gives way a little bit at a time, right? And so that kind of mechanical behavior is what enables the resilience in soils, and that's where we're going to end today. All right.
So when you build a sandcastle and you let it sit for a very long period of time, obviously you're going to have evaporative loss of water, but it still stays together. Is that because the water is never truly entirely gone? Is that has to do with the local humidity in the air, or is it the saline in the water that makes a crust? Why does the sandcastle not just relax to the angle of repose once it's dried out?
It does eventually.
Oh, it does?
Yeah.
Okay.
So if you ever look at sandcastle competitions where they keep them up for days, they come back and they rehydrate, right? And so, of course, it starts drying from the outside in.
Yep.
So you do have a side note on drying sandcastles. Essentially, you have a shallow depth over which the material is within the capillary length, which means that it gets drawn out to the surface where it can evaporate. But that depth is not very deep. And so what happens actually is you'll notice that the sharp corners and edges start to go away first, so you get a little bit of crumbling, but the core is still wet. So when you have the dry material and you spray it and you mix it around, you try to mix it around so that it's on top all the way to the interior. Of course, people like us, you can also just dump water on top and start manipulating, but you're going to get a more clumpy sandcastle, right? So the experts are spraying and manipulating, and what they're trying to do is to make the moisture most uniform everywhere. Then it starts drying from the outside in, but it's a slow process. And so if you can keep rehydrating the outside, all the water you add to the outside will gradually get drawn into the inside to replace any that's pulled away. But yeah, the evaporation is a slow enough process that you can leave a sandcastle even for a couple hours, and what you'll notice is that it starts to crumble at the sharp edges first, and then you'll see a crack somewhere, and then you come back and the crack is later, and then you'll see a piece has fallen off. So it's just a time scale kind of thing. However, you're right. If the water you're using is salt water, when it dries, you're going to leave salt bridges, and so there will be a residual cohesive stress, because there's literally crystals of salt that are bound between the sand grains. And so you can get some residual stress that way. And so you have modified the sand. It's not, if you have a tiny sandcastle, maybe it helps. For a big sandcastle, it's not enough to keep it all together. But you do raise a good point that if you're using salt water and it's evaporating, you are going to add a little bit of residual cohesion even when the water's gone. Yeah. Yeah.
Could you say a little bit more about soil in areas where you get frost or snow during certain months of the year versus that you do?
What's that?
Said John can. John loves permafrost.
Yeah.
It's I imagine the entire energy landscape, or even the little diagram we have of stress versus strain, changes on some sort of monthly cycle.
Yeah. So, first of all, so we're talking generally about permafrost or permafrosty areas, right? And yeah, John's on the line. I'm always self-conscious whenever I'm talking about anything that someone in the room knows more about, but at some point I'm always talking about something that one of you knows more about than me. So, apologies, but I'm the generalist, right? But, so, the thing, first of all, with, so let's just draw a soil surface here. So, permafrost, let's say we're in the summertime. We're up in the Arctic and it's summertime, right? So there will be a layer deep enough, let's say 1 meter down, order a meter, right? So in the summertime, the surface layer gets thawed, right? And you have this weird, mushy, squishy, active layer, as they call it. And this is nasty mud in a lot of places. And I've been to the Arctic in places where, like, in the wintertime, it's frozen all the way up to the top. In the summertime, the sun is up there, it heats from the top down. The permafrost is the part that never melts, or at least is stable over several years. Right. And so in regions where you have permafrost, there's these zones that are always frozen. And they're now going to have a mechanical behavior that is dictated by the soil constituents plus ice plus presumably some amounts of liquid water mixed in, right? This material in the top is material that in the winter was frozen, is not identical, but is kind of like this underneath. And then in the summer, there's no more ice in it, and then it's now just a squishy mud. And so you'll see this loose, squishy mud everywhere in the summertime, right? So are you asking about the mechanical behaviors of this stuff down here, like this permafrost, or this stuff when it thaws, or?
In some sense, I was like, when you have a hierarchical structure with the soil,
Yeah.
is the presence of melting and the solidifying process change that hierarchy in some way and permanently alters it or not?
Yes. Okay. So first of all, this is just to get a little geological for a second. And this is like why one of those weird things with climate change is we're worried about weird bugs that might be wrapped up in permafrost that are coming out now. The soil that's there in these places formed a long time ago. So in a lot of permafrost areas that have soil, I just made the argument to you that if you go to Antarctica, you're not going to see complex soil. Why can I go to like permafrost areas and find rich, thick soils, right? The idea is that when the climate was warmer, in the last greenhouse condition, you made these soils, and then they got locked up, both literally frozen and also figuratively frozen, like kind of frozen in place under ice age conditions, right? The reason I bring that up is that if you have complex hierarchical soils in a place that is now permanently frozen, they didn't form in a permanently frozen state. They formed in a more temperate state, and then they were frozen that way. So a lot of things change. So soil that sticks around for a long time turns into peat. It just gets compressed and congeals and almost becomes more like a deformable paste again. Like the individual, if there's organic material in it, the particles start to become undefined and it starts to congeal into like a smushed up paste. So that's a thing that happens. And so now you're increasing the length scales of interaction. Like if you have something like peat that's developed with organic matter and compression, that develops over thousands of years, but it is changing every aspect of the structure of the soil. Because you might have had fine particles just mixed with organic material, but now it's congealing into like, yeah, this kind of almost totally solid paste, right? But the other thing is that this frozen material, once it starts to get exposed, it starts cracking. So like with climate change, it's both thawing, and so it's thawing and it's just losing the ice that's holding it together. But it also can experience thermal stresses, and so the thermal stresses, because there's a lot of ice in here, it can actually cause cracks to propagate in here, even though this might be a soil that otherwise would be complex and soft and wouldn't crack all the way through. But now that you've frozen it, it can develop cracks that go all the way through. So yes, it changes kind of every aspect of the hierarchical structure, but in ways too complicated to have any sensible theory about, you know. Yeah. Yes?
Question about climate change.
Yeah.
So you were talking about how these barcans form because there's a predominant wind direction and wind strength that causes them to have a set length and shape and all that good stuff. Mm-hmm. With the way that climate change forces environments to the extremes and tends to kind of erase steady state in some places, what would you expect to happen?
I'm a human, okay?
That's going into YouTube.
Yeah.
What would you expect to happen to these barcans in a situation where climate change changes the wind conditions in their environment?
So Andrew Gunn wrote a paper about this.
Of course he did.
Just
asking.
No, but the short of it was actually, because climate change is complicated. As it turns out, under the, under the climate forecasts, let's see. in the most recent, intermodal comparison of a bunch of climate models that Andrew put together to look at the winds, it happens to be that in arid environments where dunes are, that the winds are generally slowing down, predicted to slow down. So, yeah. So there are other places where winds are getting more extreme, for example, where we are. But it seems like in deserts that there's a prediction that dune activity is going to go down. That the winds are going to get slower and the air is going to get a little more humid. And there's other places that are getting drier and the winds are going to get faster. But yeah. But indeed, I mean, they're nice. They're nice indicators of climate, because it's not just like that the wind's near threshold. It's that it's dry enough that there's no liquid bridging among grains, that there's no clay precipitating. They have a direction to them that tells you which way the predominant wind was going. So yeah, they're really nice climate indicators.